Okay, I'm going to be discussing comprehensive synchronous high-frequency measurement of InfiniBand networks in production HPC systems. And this work was done in conjunction with Ben Allen and Serge Polovitsky. In this talk, I'll be discussing what we're doing with high-frequency fixed interval sampling, how we learned how to sample at high frequency very large quantities of IB network switch ports. I will be demonstrating our sampler on a very large Sandia HPC system with InfiniBand. I'll show some initial results of our sampling, and I'll conclude with questions. So the first question, everybody says, why do we care about doing lots of high-frequency sampling? And this is our little thief that's hiding in the network. We can't see him. He's robbing our performance. It could be a user that's writing programs that cause congestion with large I/O. And then you get the usual things on a big HPC system, like switches failing and random unexpected issues cropping up periodically. By taking high-frequency samples of IB switch ports, we can correlate performance data with user job runs. We can also use that information to learn things about networks that we can use on new HPC systems, and we can ID system events and issues. So I'm going to go back to my EE background a little bit. How many people have watched old movies? You know, you see the wagon wheel going backwards. The reason it's going backwards is because we're not sampling at a fast enough rate of speed, and so we're getting bad information. The wagon wheel looks like it's going backwards instead of forwards. And we had the same thing with an HPC system. One thing we're finding in production is that we're on a normal system at Sandia, we're sampling maybe once every 3 minutes the system, and we're getting little information out of the system, or we're getting incorrect information. So we wanted to make sure we were getting better data. So when we go to meetings and people start asking questions, why did this happen, or why did this happen, we can give them that information back. There is a challenge to doing this, though. One of the challenges is we don't want to interfere with user programs. We don't want people calling in and saying, hey, why did my job take so much longer, and we're the culprit behind the problem because we're doing so many samples, it's affecting the user job run times. And in the same other aspect, we don't want user jobs interfering with our sampling. So there's a little bit of a challenge there. We had to do some learning over the last year to make that work. First thing is, you'll see something here. I'm going to kind of identify how this all works. You'll see we make a request for ports to a port switch processor, and it'll retrieve the port information and give us back an answer. Well, we didn't know what the optimum way to do that was, so we tried experimenting with having multiple people sending out to the same switch requests for a subset of ports. We also tried doing one sampler doing a bunch of switches. And what we found was if you have a sampler make one request to all the switch ports on the switch, it'll retrieve all those a lot faster and with less effect on user applications. So we can make one sampler sample, for instance, 36 ports on a 36-port switch and get our information back and ideally not affect the user application runtimes either. So we'll query the port. The processor inside the switch goes, oh, I need to grab this switch information. It'll go out there and do that. And then we'll get the information back from the switch. And then there's another piece of the thing that logs the information that we gathered, and so it can report it back to our monitoring systems. and that'll come through and get a response. We also found out, so what essentially happens is we'll go out and make a query for this port, this port, this port, and this port, and they'll all be gathered out of the switches. And then our logging system will come over and grab the information. And that's the spread time for what we're doing as far as the sampling times. We also found out some other information. We found out we want to sample things more locally to our sampler. For instance, if we have a node over here and it's connected to a leaf switch over here, we're gonna ideally go to that leaf switch first to get the information, so we're not traversing the whole network. That also degraded our sampling times. We also try to stay local. If we have on our big systems, obviously we have several tiers of switches, and we have a lot of switches in the area. So what we'll do is we'll identify nodes and then connect to the switches in that area and gather the information, so we're not, again, traversing the network. So how did this work? Well, this is a Skybridge. This is one of our big production clusters at Sandia. Last summer it was rated 381 on the 500. And this is kind of a small synopsis of what we've got with Skybridge. You'll notice we have compute nodes connected to leaf switches to a spine and a core. It's a fat tree. And you'll also notice that there's no connection between the leaf switches or the spine switches or the core switches. Everything goes up and goes down. So if we have a sampler here, for instance, it'll go up here, you'll hit a spine, maybe the core, and then it'll also look at other leaf switches that are connected to that spine switch. And if it goes up another level, we'll check the spine switches. Results. So, did this work? Yes, it did. We found out if we have 10 samplers doing 6,000 switch ports on Skybridge, that we could actually sample at ideally 75 hertz. So we could actually, we're sampling at 3 minutes currently. We can actually sample at 75 hertz. So that's a lot faster turnaround time. We can get more information out of our metrics. It takes about 1/4 of a second to sample, at worst case, those ports. So, and we were aiming for 1 second turnaround time. Now, on the extreme, let's say we had one sampler sampling 6,000 switch ports. We did try that. It took 6 seconds, but even so, that's still a 10-second sampling time, and that's still way better than 3 minutes. We also were checking to see if we were affecting the network with all those queries, and we did not detect anything. So what do you do with this information? Well, this is a 3-minute sampling. Because again, this is not 3-minute sampling. This is a 3-minute window, and we can drill down. So we can expand and get a trend, or we can drill down and really see fine details. At 3 minutes, this is what those samples look like. Now we expand out the time interval, and you can see a trend. You can see things didn't really change too much at that time period. We do see some changes here and there, but for the most part, things trended out the same. And then if we want to drill down to a specific window of time, this is at second intervals. We can see very fine details. So if somebody does something crazy or something happens, we'll see it. And we did find some, oh, I went too far, too fast. We did find a random issue too. So we found out that there was, and Serge will talk about that a little bit in his talk, but we found out that there was something crazy going on in the system. that nobody ever noticed before. One of our nodes periodically sends out and does a whole bunch of work on VL15, actually, and affects the system. Nobody's ever seen that. We've had random weird stuff before on Skybridge, and we didn't know why. And now we know that this one thing is happening every, 10 minutes. So, in conclusion, we're able now to find events happening, and we're able to, like I said, drill down and see trends, expand out and see trends, drill down, see fine details, and we're expecting that we'll learn a lot more stuff as we go forward. The sampling we can do every 20 seconds. With 10 nodes, we can do it at a 1 hertz frequency. If we have one sampler, it can be done at a 10-second frequency. This is the event that I was talking about earlier with the issues that showed up out of that we'd never seen before. I'd like to acknowledge Steve Monk. He gave us permission to install our samplers on the big production cluster. And then Mark Schmitz and Joe Mervini at Sandia, they helped us install the sampler so we could get it running. Does anybody have any questions?
Thank you. That's a very nice talk. So, did you guys measure the impact on the fabric? So, in the last slide, you mentioned that there was some nodes sending a lot of data on VL15. Now, all of this data collection by 10 samplers is going to have the same impact, because I guess all of these things.
We actually found that wasn't the case. We did a lot of research before we put this on the production system. We had to, because they just weren't going to let us randomly stick stuff on there.
Right.
We found out that if we sample at 1 hertz and we do it in a certain way, that we will not affect the job runs. It does not. We saw where it does. If we sample at 10 faster than 10 hertz, for instance, then we will see some effects.
Okay. So, like at this frequency, the amount of data going over VL15 was not big enough or large enough to affect the data traffic on the network.
Nope, that's correct.
Okay.
That's very correct. We did, like I said, they wouldn't let us stick it on the production system without checking things out.
Don't forget, VL15, this traffic doesn't go over VL15.
Oh.
Not performance management data doesn't go over VL15,
so
only subnet management traffic.
Okay, so this is then going over to VL0 along with all of the data traffic?
Yeah, potentially.
Okay.
So did you figure out what that host was that was putting out so many VL15s?
We did.
Was it the subnet manager?
It was a subnet manager is involved with it. There's some weird stuff with the subnet manager, though. So
what's the sweep time for it, by any chance?
That's it, 10 minutes.
Yeah.
So are you trying to integrate it into perf query? I mean, like, it's probably quite useful. I've worked with perf query quite a bit, so it would be useful to have it in there if you have better sample or better implementation for querying.
The difference for what we're doing is we're taking these intervals. We're using something called LDMS to gather and log the data. And LDMS samples gives you results on a fixed interval. So we can use that as the big difference between perf query samples and what we're doing with LDMS is we're actually able to log specific events at a specific time and then go back. We can do it real time or go back later, a month or two from now if we need to, and look at exactly what was going on exactly at that second.
Yeah, but you could basically do the same with perf query if you attach a timestamp.
You'd have to attach a timestamp, but here's a problem. You have, with what we're doing, it's actually at an exact fixed interval. And if you go back and attach a timestamp to perf query, you're going to have to go out at 1 second intervals and then timestamp it. And that's going to be a lot more overhead. With what we're doing, it's already, the framework's already there. We're using the framework.
Okay. And another thing, since as I said, I was working with similar things for routing issues to use counters. And what I figured out is that you cannot correlate traffic, especially higher up the tree, with your jobs. it is basically impossible to say which job is causing that traffic. Unless you have like a point-to-point, which...
We have point-to-point. So we can actually go switch port to switch port. We can go HC8 to switch port.
But you don't know which job or which job is causing that.
Yeah, we do. With LDMS, we're logging. We're taking Slurm, and they have a job ID to that Slurm.
Yes, I know, but it's still impossible. And the only way you can correlate which job is causing that is if you analyze the job location at the same time with the routing information.
Yep.
And also with how the job is actually communicating. So you need to know how the communication pattern internally is structured. So the only way to do that is if you track every message and analyze every destination lit for every message.
And we're able to do that. We're doing that.
That is a lot of tracing overhead.
We are getting 6 terabytes of data.
Okay. Yeah, if you collect that much of...
Yeah,
okay.
we're logging that much data.
Okay.
So we're getting all that information.
But then your collective will be slow as hell.
Oh, no, actually, because of the way we're doing it, we're doing a sampler for such and such. We're doing a sampler for the IB traffic. We're doing a sampler for something else, and then we're able to pull that data together, analyze it after the fact.
Thanks.
I have a couple of questions. So you mentioned that you had the samplers running on multiple nodes. Was there any reason why you just didn't launch like 10 samplers on one node? Was the bottleneck identified as the NIC?
Well, you want to distribute out your load across the machines. And then also, here's the other thing. Remember, I went back to that one slide. I was showing you want to stay local to the switches.
Okay.
We experimented. We wanted to see what our limitations were going along with what you're saying. And so what we did was we stuck 10 samplers on one node, for instance, and then went out all the way across the network. And that was very poor performance. It took a long time to get the data back, and then things were interfering with each other, and then we degraded our performance on the jobs.
Okay.
But if we stay local, if we distribute things out, we can go and pick out things that are locally connected, or are a little further away maybe even, and then we're not doing that.
Okay. So one other question is, I don't exactly recall how LDMS does it, but I think it runs at 1 daemon per compute node. So how is it able to figure out the actual data that MPI process 1 sent this data to MPI process 10 on a different node?
So there's aggregators, and what they do is you'll set the aggregator. You'll say go to this node and gather this data, and then they'll go eventually down the pipe, and it'll go to a logging system. It uses usually a comma separated value, spits out a whole long list of data.
Right, I understand that, but unless you have information from the MPI library, all you can figure out is this node sent out so many bytes. You will not have the information saying that this node sent out so many bytes to this end node, because that information, to the best of my knowledge, is not exposed by the low-level performance counters. And I think that was the point that he was trying to make.
I was saying you have to analyze for every IP drops post-send call, you have to analyze the destination list for every single message. And in collective, you cannot do that because like do an all-to-all with like bunch of gigabytes. You will have like tiny little messages, hundreds of them for every destination. So you're effectively getting millions of millions of data points within one all-to-all already.
Yeah.
Each node.
Mm-hmm.
That will like crush the performance of the all-to-all. It will completely destroy the performance. And like that is something to do analysis if how the collective internally is structured. But
So here's the deal. So you're assuming my sampling is affecting the data traffic.
no, your sampling will affect the performance of
The all-to-all?
yes.
We haven't seen that. Again, we did all-to-alls. We did all types of different MPI commands. We did all kinds of different network traffic, and we did not see that.
Sorry, just to clarify, I agree with you that yes, we definitely can do this, but my only question was how was LDMS able to do this on a peer-to-peer basis? So, like, is that possible, or did I misunderstand the statement? So, can the system say that MPI rank 1 sent data to MPI rank 10 on a different node, or is the granularity that node X sent out so many data and received so much data? So I just want to figure out what the granularity is.
The granularity is that they'll send so many packets, they'll see so much traffic, they'll congest so much data at a specific point in time. And then we can, like I said, we can see what the job is that ran that data. We can correlate it to that at this point and look at their instructions later if we have to.
Yeah.
We can say, oh, this happened at this time. Well, what's going on in this job?
Sure.
What did they do? What did they write? Is he doing a ton of I/O to the disk, or is he doing an all-to-alls on every step?
Sure. Yeah. So yeah, that answered my question. And just for the record, I agree that yes, you definitely can sample any communication without significantly affecting the performance of it. So yes, I agree with you on that. Just to be clear.
Okay.
Thanks.
Depends how deep down the tree you're sampling.
We can take it off.
Okay.
Okay. All right, I'm gonna step back to my other shoe.